Hi everybody, this is the lecture on section 8.2 on infinite series. Okay, given a sequence, so in section 8.1 AN, right, which starts at 0 or starts at 1 or whatever it might be. Okay, given a sequence AN, okay, an infinite series, or just a series, is the sum of the sequence. So you write the sum n equals 1 to infinity, or n equals 0 to infinity, an, which is a1 plus a2 plus a3, so on and so forth. All right, well, you know, the sequence is when you just look at one term at a time. The series is when you try to add those guys up, right? So they better be very tiny if they're going to add up to something meaningful. So, for example, right, consider this rectangle here, 2 by 1. This is a 2 foot by 1 foot rectangle, 2 meter by 1 meter, whatever you like. All right, so this is 1 by 1. Right, this is 1, this is 1, the whole thing is 2 by 1. So the area here is 1. Right, and the area here is 1. The area here is a half. The area here is a quarter. The area here is 1/8. The area here is 1/16. The area here is 1/32. And the area here (1 over 64), so on and so on and so forth. And eventually, I mean, you know, this is going to take up the entire square, right? So, or rectangle, sorry. So from here, the sum n equals 0 to infinity, 1/2 to the n, which is equal to 1 plus a half plus a quarter plus an eighth plus a 16th, so on and so forth like that, is equal to 2. Because it's just the area of this whole rectangle, right? So even though there's infinitely many sums in the term, you know, you do get an actual meaningful sum, finite sum, right? And this is just one real nice example of that. Okay, so in general, how can we define sum n equals 1 to infinity an and tell whether or not it exists? Okay, and the way to do that is through partial sums. Okay, so given the infinite series, the sum, let's start at 0 this time. We could start at 0. an, which is equal to a0 plus a1 plus a2 plus a3, so on and so forth. Define the kth partial sum as the sum n equals 0 to k an, which is a0 plus a1 plus a2 all the way up to ak. Now that is defined, right? It's just a finite sum of finite numbers, and we know how to deal with that. So let's give this a notation as well. So we'll call this SK. So the kth partial sum. Okay, or you can call it PK, partial sum. Define, close my email. Define the sum n equals 0 to infinity of an. So define the infinite partial sum as the limit of, define the infinite sum as the limit of the partial sums, if it exists. Okay? When it exists, we say that the series converges. Converges. When the limit is infinity or does not exist, we say that the series diverges. All right, same sort of vocabulary that we've been using with these limits, right? With improper integrals and with series. And as you'll see, this idea of an infinite series is very much tied up with the idea of the improper integral from 1 to infinity. So well, there's a whole section dedicated to that. All right. So, by the way, so this is similar to the idea. Let me just write it down. All right. Notice the similarity between, right, the sum n equals 0 to infinity an is the limit as k goes to infinity of the partial sum, and the integral from 0 to infinity fx dx is equal to the limit as k goes to infinity integral from 0 to k fx dx. Right? Notice that similarity. And in section, what section is it? In section 5.3, we'll really formalize that similarity and talk about what sort of things you can get from it. Okay. Now, in general, it's very hard to get solutions to actually calculate the sum of an infinite series. There are a couple different times where you can. So first, let's talk about the geometric series. Okay, given so the geometric series with ratio r is the sum, well, maybe it starts at 0 of the powers of r, or starts at k r to the n. All right, so powers of r starting at r equal to 0, or powers of r starting at r equal to k. Can we calculate this? Geometric series is one series that we can actually evaluate. Okay, so there's only going to be like 3 or 4 examples of series that we can actually evaluate. Okay, in chapter 5, there's only 2. Geometric series is one of them. Okay, and the what's the other one called? Telescoping series is the other one. Only 2 types: geometric and telescoping. Okay, in chapter 5. In chapter 6, we'll get a few more. But those have to do with the elementary functions, sine, cosine, e to the x, and square root of x, and things like that. Okay, so the geometric series is one of very few series that we can actually evaluate. Okay, so let's talk about the partial sum. So given the standard geometric series, sum n equals 0 to infinity, r to the n, the kth partial sum is pk sum n equals 0 to k r to the n. So this is 1 plus r squared plus r to the k. So powers of r up to r to the k. Now, we can actually get an expression for this in terms of k. So this is equal to 1 plus r squared all the way up to r to the k over 1 minus r times 1 minus r. Yeah? All right, I'm just doing an uncancellation like that. All right, well, let's multiply and see what happens. So 1 times all of this minus r times all of this, which is r plus r squared plus r to the k plus 1. All right, let me put over 1 minus r. All right, but now we have cancellation. The 1 doesn't cancel with anything, but here we have plus r minus r, plus r squared minus r squared, plus r to the k minus r to the k. So everything cancels except for this 1 and this r to the k plus 1. So this whole thing is equal to 1 minus r to the k plus 1 over 1 minus r. Okay? So that's the partial sum, kth partial sum for the geometric series. So now, if r in absolute values is less than 1, right, like a half, like a third, like 9/10, negative 9/10, negative 1/2, negative 1/3, as long as r is less than 1, okay, r to the n must converge to 0 because it keeps getting smaller, right? Whenever you multiply by a number less than 1, it just keeps getting smaller. And this one goes all the way to 0, right? A half, a fourth, an eighth, 16th, 1/32nd, 1/64th, 1/128th, so on and so forth. These things keep getting smaller and smaller. If r is equal to 1, then, well, r to the n is 1 to the n, which is just 1. Well, let me leave that one out. If r is bigger than 1, then r to the n, well, it diverges. It goes to infinity. Or it diverges. Especially if r is negative. So, okay, okay, when r is less than 1, the sum n equals 0 to infinity, r to the n is the limit as k goes to infinity of the partial sum pk, which is equal to the limit as k goes to infinity 1 minus r to the k plus 1 over 1 minus r. But this one is 0, so it's 1 over 1 minus r. And later on, we'll talk about when r is bigger than or equal to 1. The series diverges. Okay, we'll talk a little bit more about that and why it actually diverges a little bit later, but let's concentrate on the situation where the absolute value of r is less than 1. In this case, right, the geometric series is the limit of the partial sums, and the partial sum had this expression as k goes to infinity. That's 1, that's 1, that's r, and that goes to 0. So that's the sum, 1 over 1 minus r. Right, for the geometric series that starts at n equal to k, or n equal to t, also, when r is less than 1, absolute value of r is less than 1, the sum n equals t to infinity, r to the n, is equal to, well, it starts at r to the t plus r to the t plus 1 plus r to the t plus 2, infinite series like that. But these all have a common factor of r to the t. And then you're left over with 1 plus r squared plus r to the third, so on and so forth like that. But that's just the original geometric series. So this is r to the t times the sum n equals 0 to infinity, r to the n, which is equal to r to the t times 1 over 1 minus r. So this is equal to r to the t over 1 minus r. So that's the summary. In summary, if absolute value of r is less than 1, then the sum n equals 0 to infinity, r to the n, is equal to 1 over 1 minus r, and the sum n equals t to infinity, r to the n, is r to the t over 1 minus r. So that's the essential property of the geometric series. Okay? If that ratio is less than 1, then the geometric series starting at r to the 0 is 1 over 1 minus r, and the geometric series starting at r to the t is r to the t over 1 minus r. So, for example, right, the sum n equals 0 to infinity, 1/2 to the n, right, that rectangle. Well, 1/2 is less than 1, so that's 1 over 1 minus 1/2, which is 2. Sum n equals 0 to infinity minus 1/2 to the n. Well, that's 1 over 1 minus 1/2. Right, which is 1 over 3/2 is 2/3. How about this? Sum n equals 2 to infinity (3 to the n). Well, let's do 0. That's fine. Do 0. 3 to the n plus minus 2 to the n plus 1 over 5 to the n is equal to, well, it's not a geometric series yet, but let's split this up. So this is 3 to the n over 5 to the n plus minus 2 to the n plus 1 over 5 to the n. So we're splitting up the numerator over the denominator. So example 1, example 2, example 3. So this is equal to, well, sum n equals 0 to infinity. 3 to the n over 5 to the n, well, that's 3/5 to the n. Plus, let's factor out a minus 2. Minus 2 minus 2 to the n over 5 to the n. Right? Minus 2 to the n plus 1. Peel off one factor of minus 2. Now I have minus 2 to the n over 5 to the n. Why did I do that? Well, minus 2 to the n over 5 to the n is minus 2/5 to the n. It's like we did here. 3 to the n over 5 to the n is 3/5 to the n. So this is equal to the sum n equals 0 to infinity 3/5 to the n minus 2 times minus 2/5 to the n. So I have a sum of a sum. But addition is commutative, so we might as well split them up like this. In this sum, there's a common factor of minus 2. So I can factor that out of the sum. Minus 2 times the sum. N equals 0 to infinity minus 2/5 to the n. Right? That's a geometric series with ratio 3/5. So its sum is that. Minus 2, geometric ratio series with ratio negative 2/5. Negative 2/5 again, less than 1. So that's 1 plus 2/5. So the sum in general is going to be, so that's 2/5, 5/2, minus 2 times 7/5, 5/7. So what do we have here? 5/2 minus 10 over 7. So 35 minus 20. 35 minus 20 is 15 over 14. Okay? And so that was example 3. Example 4, sum n equals 1 to infinity. 1.2 to the n. That one diverges. Because 1.2 is bigger than 1. Okay? So, several examples of working with geometric series. Notice what we did here in example 3. Okay, two things that we did. We took the sum of a sum and made it into two, the series of a sum into two series. And the series that had the constant factor, we factored it out. Right, so you can do that in general, right, because it's just basic properties of addition. That we used the following two properties. In example 3. above. One is that the sum n equals 0 to infinity an plus bn, like this, is the sum n equals 0 to infinity of an plus the sum n equals 0 to infinity bn. And 2, the sum n equals 0 to infinity, some common factor t times an is t times the sum n equals 0 to infinity an. Alright, so a couple basic properties about working with infinite series. Working with infinite series is just about dealing with sums and with limits. We know the limit of a sum is the sum of the limits, right? And that addition, of course, is commutative. And right, the limit of a sum, the limit of a constant times a function is the constant times the limit of the function, right? So that's just two properties we know about with dealing with limits, and they apply here with infinite series, because infinite series are defined using these limits. All right, so that's the geometric series. So that's one type of series we know how to deal with. One type of series that we know how to deal with in Chapter 5. There's only one other series that we know how to actually add it up. Geometric series. We know what the sum is. That's one. 2 is what's called a telescoping series. So actually the geometric series is a telescoping series, but there's something a little bit more general with telescoping series. Let me find my example that I have. Here it is. So a telescoping series is telescoping when every term in pk cancels out except for some finite number of them. That's what happened with the geometric series when we were finding the limit for the geometric series. Right there. The partial sum is 1 plus r squared up to r to the k. And then we rewrote it like this. And then we distributed this over the 1 minus r. And we got this sort of thing here. So the r's cancel, the r squareds cancel, the r to the thirds cancel, all the way up to r to the k's cancel. And all that's left is the 1, the first term, and the last term. Like that. Alright, so that's an example of a telescoping series. And when you have a telescoping series, hopefully you'll be able to evaluate the sum. Alright, so here's an example, another example. The sum n equals 1 to infinity 2 over n times n plus 2. Okay, using partial fractions, so here's partial fractions again. 2 over n times n plus 2 is equal to a over n plus b over n plus 2 is equal to a times n plus 2 plus b times n over n times n plus 2. So, right, what do you get? If you let n equal to 0, right, then you get 2a is 2. So a is 1. And then if you let n equal to negative 2, you get negative 2b is 2. So b is negative 1. Thus, 2 over n times n plus 1 is equal to 1 over n minus 1 over n plus 2. So now, let's look at the partial sums. Let's find the partial sum, pk. So let's start with, well, the partial sum pk for this infinite series. So I'm going to need to refer to that. So let me put it here so I don't have to keep scrolling back and forth. Let's find the partial sum. There we go, for this infinite series, okay? All right, well, let's you don't have to start at P1. Let's start at, say, P3. So the third partial sum. Well, first of all, okay. Oh, well, I guess I better write it this way. For this, which is equal to the sum n equals 1 to infinity, 1 over n minus 1 over n plus 2. Like that. So let's look at the third partial sum. So the term for n equal to 1 is 1 minus a third. Plus the term for n equal to 2 is a half minus a fourth. Plus this term for n equal to 3 is a third minus a fifth. Right? So the minus 1/3, the plus 1/3 cancels. And I'm left with 1 plus a half minus a fourth minus a fifth. Let's calculate the fourth partial sum. Well, the fourth partial sum, it's the third partial sum. Plus the term for n equal to 4, which is a quarter minus a sixth. So minus a third plus a third, minus a quarter plus a quarter. And I'm left with 1 plus a half minus a fifth minus a sixth. That's the fourth partial sum. How about the fifth partial sum? Well, the fifth partial sum is 1 minus a third. It's the fourth partial sum. Plus the term for n equal to 5, which is a fifth minus a seventh. So plus minus a third plus a third, minus a quarter plus a quarter, minus a fifth plus a fifth. So I'm left with 1 plus a half minus 1/6 minus 1/7. All right, so in each of these partial sums, can we say what pk is now? Therefore, we see that pk is equal to. All right, well, each of these partial sums has got 1 plus a half, 1 plus a half, 1 plus a half. So probably that's going to be there. The third partial sum has minus 1/4, minus 1/5. The fourth partial sum has minus 1/5, minus 1/6. The fifth partial sum has minus 1/6, minus 1/7. So the kth partial sum is going to have minus 1 over k plus 1 minus 1 over k plus 2. So there it is. the kth partial sum. And we've got it as a function of k. So now, the sum n equals 1 to infinity of 2 over n times n plus 2 is equal to the limit as k goes to infinity of pk. But that's the limit as k goes to infinity of this. 1 plus a half minus 1 over k plus 1 minus 1 over k plus 2. This is 1, this is a half, this is 0, this is 0 as k goes to infinity. So that's 1 plus a half plus 0 is 3 halves. So that telescoping series converges to 3 halves. And you can see where this term telescoping comes from, right? In the partial sum, all the junk in the middle cancels out, and all you're left with is the first couple terms, stuff from the first couple terms and stuff from the last couple terms. So if you think of those old, telescopes that, they used on naval ships in the 18th century, those collapsing telescopes, right? You have the big old telescope, and then you collapse it, and everything in the middle kind of disappears, and all you're left is with the beginning and end of the telescope. So that's where the term comes from. Kind of a cute term. All right. Another telescoping series as follows. Sum n equals 0 to infinity. Natural log n over n plus 1. Right? Well, the partial sum, pk, is equal to, and I'm just going to write out the whole thing. Right? It's not starting at 0, sorry, starting at 1. It's natural log 1/2 plus natural log 2/3 plus natural log 3/4 plus natural log k over k plus 1. I'm just going to write out the whole thing. Nothing's telescoping yet, but remember the log of a fraction breaks up into a difference of logs. Like that. Oops, natural log k plus 1. The natural log 2's cancel, the natural log 3's cancel, natural log 4's cancel, all the way out to the natural log of k. Everything in the middle there cancels out, and we're left with natural log of 1 minus natural log k plus 1. That's 0. So it's just minus the natural log of k plus 1. So the the sum n equals 1 to infinity natural log n over n plus 1 is equal to the limit as k goes to infinity minus natural log k plus 1. But as k goes to infinity, right, this is the natural log of infinity. But the natural log of infinity is infinity. So this thing is minus infinity. So the sum diverges. That telescoping sum. So not that a telescoping sum has to converge. It certainly doesn't have to. And there's an example of where it doesn't. All right. Lastly, so that's it, by the way. So as far as in chapter 5, series that we know what the sum is, okay, it's telescoping and geometric, and that's it. Everything else, can't tell. With the techniques of chapter 5, we We can estimate, and we'll talk about that. We can estimate sums, and we'll talk about how to estimate sums. We can tell when sums converge and when they diverge, okay, but actually what they converge to, we may not know. Okay, we'll talk more about that, but I mean, as far as getting the actual sum, only these two types. Geometric, telescoping, that's it. All right. Theorem. If the series converges, then the terms must go to zero. If a series converges, then the terms must go to zero. This is more interesting when you state it in the contrapositive. So in a logically equivalent form called the contrapositive, we have if the terms don't converge to zero, then the series does not converge. It diverges. Okay? So, convergent series, the terms must go to zero. If the terms converge, I mean, the terms might converge to 3 or something like that. If the terms converge to 3, then the series will diverge. Or if the terms don't converge at all, the sequence of terms. There's a difference between sequence and series. Please don't get them confused. If the sequence converges to something non-zero, or the sequence diverges, the sum diverges. Okay? Should I do the proof of that for you? Let me give you an example, and then I'll show you the proof. So, for example, something like this: 3n plus 1 over 2n minus 5. That converges to 3 halves. This sequence converges to 3 halves, which ain't 0. Therefore, the sum, n equals, well, starting where? N equals 3 to infinity, so this is not 0 there. Well, it never can be. Yeah, that's fine. N equals 0 to infinity, 3n plus 1 over 2n minus 5 diverges. Okay? So that's an example. Don't turn it around. Don't get it confused. Okay? Another example. So we'll prove it in the next section. So in the next section, we will show that the sum n equals not 0, 1 to infinity, 1 over n diverges, even though 1 over n goes to 0. Okay? Don't get the implications mixed up. You can never turn around, not never, but you can't really turn around an implication. Right? If the series converges, then the terms go to 0. Not if the terms go to 0, then the series converges. Right? They're not the same statements at all. For example, so the usual example I say doesn't work during a pandemic. What's the usual example I give? It's a different example. So, okay. So my name is Daniel Slilotti, right? So if your last name is Slilotti, which it isn't, but if your last name is Slilotti, then you're a relative of mine, right? If your last name is Slilotti, then you're a relative of mine. Correct. We're all relatives. If you're a relative of mine, then your last name is Slavati. Incorrect. I have relatives of different names. My cousins, right, have different last names. My aunts and uncles, different last names. Okay? So you can't turn around an if-then statement. They're not logically equivalent. They're a containment. If P, then Q means P is contained within Q. But if P is contained within Q, Q is not contained within P, unless they're actually the exact same thing. But that's not the case here, right? So if the terms don't go to 0, then the series diverges. Or if the series converges, the terms go to 0. But if the terms go to 0, it doesn't mean the sum has to converge. And this is the standard example. All right. Let's go over the proof of that. Okay, so proof. Suppose that S is the sum n equals 1 to infinity an, which is equal to the limit as n goes to infinity of the, or as k goes to infinity, of the partial sum pk. Right? So S minus S is the limit as k goes to infinity, pk minus the limit as k goes to infinity, pk. But k is going to infinity. K is going to infinity. So if I delay going to infinity by one step, it doesn't really matter. I'm still going to get there. Right? I mean, if k goes to infinity, so does k minus 1. So the limit as k goes to infinity of pk is the same as the limit as k goes to infinity of k minus 1. Because if k goes to infinity, so does k minus 1. Same sort of thing. But, oh, and then s minus s, of course, is 0. The limit of a sum is the sum of the limits. Right? And what's the difference between the 10th partial sum and the 9th partial sum? The difference between the 10th and the 9th partial sum is the 10th term. And that's, so the limit between, the difference between the kth partial sum and the k minus first partial sum is just ak. So there it is. So ak converges to 0. And we're done. Okay? So that's the lecture on this section.